Okay, hello and welcome back everybody. So this is the worked example section for Hermitian and symmetric operators. We'll go through basically the reason why these matter is that we try to employ the spectral theorem, which let's just recall really quick. It says that a Hermitian operator can be decomposed as a unitary diagonal in the adjoint of the unitary, and a symmetric operator can be orthogonal diagonal in the transpose of an orthogonal. And in particular, the diagonal matrices are purely real. So that's really why we care about these. And so today we're basically going to be asked to perform diagonalization, but we're going to do it in a way such that we recover unitary and orthogonal operators. So our first example, check whether the matrix 2, 1, 1, negative 2 is symmetric. If so, find an orthonormal basis of eigenvectors and decompose. Decompose is another word. It's broader than diagonalization. It's any time you represent one matrix as a product of other matrices. We'll say decompose S equals O D O transpose. So let's do it. Or we'll say where O is orthogonal. So really it's not too bad. All we have to do, the first thing we're going to do is check if it's symmetric. So to see if it's symmetric, we're going to take it and we're going to compute its transpose, which means I'm swapping the 1 for the 1. Big surprise. Yes, it's symmetric. Okay. More important, it says find an orthonormal basis of eigenvectors. So we're going to have to find eigenvectors, and to find eigenvectors, we need to find eigenvalues. We've been doing this most of the semester. It's probably the most important thing we've learned this semester. So we'll go ahead and try to breeze through it. I've got 2 minus lambda times negative 2 minus lambda minus 1 squared. It's going to give me negative 4. Then I'll have a plus 2 lambda and a minus 2 lambda. Then I'll have lambda squared, and I'll have minus 1. This gives me lambda squared. The 2 lambdas cancel. Minus 5 is equal to 0. I recover that lambda is equal to plus or minus the square root of 5. And write it as root 5 or negative root 5. Those are my 2 eigenvalues. And yes, those are both real numbers. Let's go ahead and find eigenvectors. So for lambda is the positive root 5. We're looking at the equation 2 minus root 5, 1, 1, and negative 2 minus root 5 against x1, x2 equals 0, 0. The top line is going to tell me that 2 minus root 5 x1 plus x2 is 0, which can immediately be arranged for x2 as x2 is root 5 minus 2 x1. That's my relationship. So I recover the eigenvector corresponding to root 5 as x1, x2, and because of my relationship, this is x1 root 5 minus 2 x1. If I go ahead and let x1 be 1, I have x root 5 is equal to 1, and root 5 minus 2 times 1. Now, this is an eigenvector, but it is not a normalized eigenvector. Because I was asked for an orthonormal basis, emphasis on normal here, we must normalize this vector. Now let's recall, what do you do to normalize? Well, one thing you can do is put a hat on it instead of a vector line. And you just go ahead and grab the vector and divide by its norm. So this is x as a vector divided by the norm of x as a vector. That's going to be 1 divided by the square root, 1 squared, plus, this is a little trickier, what is root 5 minus 2 squared? That's 5 because of root 5 squared. If I look at my insides, it's minus 2 copies of 2 root 5. And then that last term is plus 4 squared. So I have 9 minus 4 root 5. This will be 9 minus 4 root 5. So a little bit ugly. And this multiplies 1 root 5 minus 2. A little bit ugly. But we can write it out as, I guess that's a total of 10 minus 4 root 5 in the denominator, and we just put up with it. So we have 1 over the square root of 10 minus 4 root 5. And then my vector, 1 root 5 minus 2. So no one ever said these were pretty, but it is normalized. We do the same when lambda is negative root 5. What we end up with is 2 plus root 5, 1, 1, negative 2 plus root 5 against x1, x2 equals 0, 0. The first line tells me that 2 plus root 5, x1 plus x2 is 0, which can be quickly rearranged for x2, as x2 is negative 2 plus root 5, x1. That's my relationship. So I have the vector x corresponding to negative root 5 is x1, x2, which I know x2 in terms of x1 is negative 2 plus root 5, x1. And if I let x1 be 1, I have that x corresponding to negative root 5 is the vector 1 and negative 2 minus root 5. As before, this needs to be normalized. And it gets normalized to x hat sub negative root 5 is x vector sub negative root 5 over the norm of x vector sub negative root 5, which just as before will be 1 divided by root 1 squared, because the first entry, and then what is negative 2 minus root 5 squared? Looks like I have negative 2 squared is 4, I have negative 5 squared is 5, and I have 2 copies of negative 2 times negative root 5, so I'll have a 4 root 5 here. So a total of 9 plus 4 root 5, as opposed to 9 minus 4 root 5 in the previous case. So I have 1 plus 9 plus 4 root 5. Then I end up with 1 and negative 2 minus root 5. And to make this look slightly more like the previous one, I'll write it as 1 over root 10 plus 4 root 5 against 1 negative root 5 minus 2. And this will be my second normalized eigenvector, which gives me the orthogonal matrix, right? Part of the diagonalization now. What we have in diagonalization is my x vector in diagonalization is now an orthogonal vector, or an orthogonal matrix, and it's comprised of the 2 eigenvectors forming the columns. My first one, I will have to distribute the root 10 minus 4 root 5 to both terms, and same in the second one, I'll have to distribute that to both terms. So what do we end up with? We end up with 1 over root 10 minus 4 root 5, and root 5 minus 2 all over root 10 minus 4 root 5. And then in the second case, we have 1 over root 10 plus 4 root 5, and then the second line is negative 5 minus 2 over root 10 plus 4 root 5. And yeah, lots of roots make this a little ugly, but this is a perfectly valid orthogonal matrix, as well as D, my diagonal matrix corresponding to the eigenvalues root 5, negative root 5. Then my original matrix, symmetric matrix, 2, 1, 1, negative 2 is equal to O, D, O transpose. Okay, let's move on to the second problem, where we'll do the same thing with a Hermitian matrix. We'll basically ask the same question. So is the matrix H hat described by 1, 1 plus I, 1 minus I, 1 Hermitian? If so, find an orthonormal basis of eigenvectors and decompose H hat equals unitary, diagonal, unitary, Hermitian conjugate, where U is unitary. Okay, so just as before, but now with Hermitian, we're going to test if this is equal to its conjugate transpose or equal to its adjoint. So let's compute H hat adjoint. It's going to be my transpose as well as a conjugate. So if I go ahead and transpose, that's me looking at the diagonal and swapping 1 plus I for 1 minus I, so I'll have 1, 1 minus I, 1 plus I, and 1. Now I have a conjugate. And we apply the conjugate everywhere. We get 1 plus I. We're swapping i's for negative i's. 1 minus I, and 1, which is exactly h. So we are indeed Hermitian. And from this point, then we need to find our orthonormal basis of eigenvectors and then diagonalize. So if we're going to diagonalize, we need to find eigenvalues. So to find the eigenvalues, I need to construct the characteristic equation, which will be the determinant of 1 minus lambda, 1 plus I, 1 minus I, and 1 minus lambda. So that'll be 1 minus lambda squared minus 1 plus I times 1 minus I. So when I FOIL 1 minus lambda squared, that's not too bad. It's 1 minus 2 lambda plus lambda squared. When I FOIL this, we'll go first, outside, inside, last. We'll have 1 from the first, negative I from the outside, positive I from the inside, negative I squared from the last. These last terms all had a minus sign in front of them coming from here. There's a minus sign there. And then we'll go ahead and compute. So we've got lambda squared, total of negative 2 lambda. And then these i's cancel. And we have 1 minus 1 minus 1, also known as minus 1 here. And we're going to compute the solutions to the characteristic equation using the quadratic formula. So negative b plus or minus the square root of b squared, which is 4, minus 4ac is going to be minus 4 times negative 1 times 1, so plus 4 all over 2. It's going to be 2 plus or minus root 8 over 2. And if I want to go ahead and apply the 2 to both terms there, I can pull it inside the square root as a 2 squared, also known as 4. 8 divided by 4 is 2. So my 2 lambda values are going to be 1 plus root 2 and 1 minus root 2. If I want to go ahead and find eigenvectors then, I can. My eigenvectors are going to be the solutions when lambda is 1 plus root 2 to, well, 1 minus 1 plus root 2, right? 1 minus 1 plus root 2, 1 plus I, 1 minus I, and 1 minus 1 plus root 2. What does this give me? I can simplify 1 minus 1 plus root 2 is just negative root 2, 1 plus I, 1 minus I, and negative root 2. Against x1, x2 has to be equal to 0, 0. The first row is going to tell me that negative root 2 copies of x1 plus I plus 1 copies of x2 is 0. I can solve this for x1 by bringing negative 2x1 to the right and then dividing by root 2. I see that x1 is equal to 1 plus I over root 2 x2. And that's my relationship. So when I write the vector corresponding to 1 plus root 2, this gives me x1, x2. Or in other words, it gives me replacing x1 with 1 plus I over root 2 x2, x2. Then I can send x2 to 1 to recover my eigenvector as 1 plus I over root 2 and 1. But this does need to be normalized just as before. Needs to be normalized. So we'll go ahead and normalize it. X hat, 1 plus root 2, is going to be x vector, 1 plus root 2, over the norm of x vector, 1 plus root 2. And that's going to give me 1 divided by, what's the norm here? I square this, or I'm looking at the absolute value of that squared, 1 plus I over root 2 squared. Absolute value of complex numbers, right? We're looking at, if we're squaring the absolute value, we're just looking at the coefficients on the complex number squared. So coefficients of 1 squared plus 1 squared, 1 squared plus 1 squared over root 2 squared is 2. Turns out that that has a norm of 1. And then 1 squared is just 1 as well. So 1 plus 1, and then we multiply by our vector, 1 plus I over root 2 and 1. I have another copy of 1 over root 2, 1 plus I over root 2, 1. I could pull that to both terms on the inside. That doesn't make my life too terribly difficult. This is 1 plus I over 2, because I have 2 copies of root 2, as well as 1 over root 2. So that's my normalized first eigenvector. And the second eigenvector corresponding to lambda being 1 minus root 2. We're looking at the matrix now. Root 2, 1 plus I, 1 minus I, root 2 against x1, x2 has to be 0, 0. The top row is going to send me to root 2 copies of x1 plus 1 plus I copies of x2 is equal to 0. And this can quickly send me, I'm going to bring root 2x1 to the right with a negative sign and then divide by negative root 2. It's the negative of what I had before. So I have negative 1 plus I over root 2. in terms of x2. This is going to give me x sub 1 minus root 2 as x1, x2, but I know x1 in terms of x2 is negative 1 plus I over root 2, x2, x2, and I can send my x2s to 1, giving me x sub 1 minus root 2 as negative 1 plus I over root 2 and 1. Now when I normalize, I'm going to take a shortcut. This is very clearly the same. It's like the same vector as my earlier vector, and so the magnitude is going to be the same, noting the magnitude of this is the same as my earlier vector, 1 plus root 2, and so the magnitude of both cases is just root 2. So normalization is pretty easy. X with a hat on it, 1 minus root 2, will just be 1 over its norm, which is root 2, against its entries, 1 plus I over root 2 and 1, and I can distribute that to get negative 1 plus I over 2 and 1 over root 2. Okay, so that means when I get to producing the unitary matrix for diagonalization, if I have my Hermitian matrix, which was 1, 1 plus I, 1 minus I, and 1, will be the unitary matrix, and then the diagonal, and then the unitary adjoint. The unitary matrix will just be my two eigenvectors that I have above, so the normalized ones though, right? So the 2 in cyan there. So I have, in the first case, the 1 plus I over 2, and 1 over root 2. And in the second case, a minus 1 plus I over 2 and 1 over root 2. So that's my unitary matrix, and my diagonal is the eigenvalues, 1 plus root 2, 0, 0, 1 minus root 2. So there you go. Now, these are probably the more practical examples. This is what you actually tend to do in a lot of quantum mechanics courses, but there are a lot of cases where we do problems with operators in infinite dimensional spaces instead. So I want to give a really lovely example here, which is the construction of the Fourier series using the spectral theorem. So we're just going to start with the operator I d dx, and it's going to map L2 of the torus to L2 of the torus is Hermitian by way of the previous section. I proved this for all of you in the previous section, so if you forget where that was, just go to the previous section and find it. So this is Hermitian. Therefore, there is an orthonormal basis of eigenvectors. But vectors in our vector space of L2 on the torus are functions. So what does it mean to be an eigenfunction here? Let's look at the eigenfunctions of I d dx. I need this to hit f of x, and I need it to be equal to a number times itself. Or if I want to make this look like maybe my differential equations, I can put a y here and a y here. Or if I really want to make it look like my differential equations, let's divide by I. We end up with y prime, and then let's move every term to the left-hand side. Y prime plus I lambda y equals 0 has solutions y of x equals e to the I lambda x. It's like your matrix exponential, but it's just a one-dimensional quantity. Sorry, e to minus I lambda x. Matrix exponential, but it's a one-dimensional quantity. For lambda in the complex numbers, there's nothing requiring that lambda doesn't have to be in the complex numbers. However, we're looking for objects in this space, which you recall what this space was. It's from negative pi to pi, and it outputs me in C, but I have some restrictions. I have to be equal to myself on either side, at both negative pi and positive pi, and I need to be square integrable. The square integrability condition is not too terribly strong, so we won't worry about that condition. But let's check for which values of lambda this is satisfied. So for which lambda in the complex numbers do we have that negative pi is equal to pi? So let's just find out. Y at negative pi will be e to the I lambda pi, because the negative signs cancel. And if I want that to be equal to y at positive pi is e to the negative I lambda pi. So I need this to be true. And how can I rearrange that to be true? I could divide both sides by e to the minus I lambda pi. Same as multiplying by the positive, we end up with e to the 2 pi I lambda equals 1. And without getting into the nitty-gritty details, this is Euler's formula, right? This is Euler's formula, giving me cosine of 2 pi lambda plus I sine 2 pi lambda equals 1. It really equals 1 plus I times 0. So I need cosine of 2 pi lambda to be 1, and I need sine of 2 pi lambda to be 0. Let's go to our unit circle. How do I get cosine to be 1 and sine to be 0? That's only here. That's the point 1, 0. Cosine, sine. So it only occurs there, but where does that occur with regards to rotations? I could have 0 radians, I could have pi radian, or 2 pi radians, I could have 4 pi radians, I could also have negative 2 pi radians, or negative 4 pi radians, and continued. Okay, but that means that 2 pi lambda needs to be 2 pi z, the integers, 2 pi z. 2 pi lambdas and 2 pi z cancel my 2 pi's, we find out lambda is in z. Lambda's in the integers. So, what do we discover? We discover the orthonormal basis of eigenvectors for I ddx on specifically this special space, L2 of the torus to L2 of the torus, is e to the ikx, or negative ikx, either one's the same, where k is in the integers. So that's now an orthonormal basis, and the orthonormal basis is going to help me decompose. Let's decompose a function or vector according to this orthonormal basis. Well, that is to say that a function can be written as an inner product of the function against the basis elements, e hat k, k is in some index set. This is always the case. This is how you define decomposition of vectors. Maybe I'll make it explicit that I'm doing vectors here. I could just say v as a vector is the vector against the basis. But in our case, that's f is a function. It's the inner product of the function against e to the ikx, e to the ikx. K is in the integers. But what is that inner product? That's me writing k goes from minus infinity to infinity. Those are the integers. I can write the inner product as 1 over root 2 pi, negative pi to pi, f of x against the complex conjugate, so a negative I kx dx, e to the positive I kx. This is the Fourier series. So you actually recover the Fourier series out of the spectral theorem. Now, of course, we're not going to be testing on that. I realize it's kind of a little bit above a lot of people's heads, but it's really cool to see that this spectral theorem is kind of what births the Fourier series for us. And in fact, it births so much more than the Fourier series for us. Turns out every Hermitian operator has its own Fourier series, and that's really, really cool. That is how we do quantum mechanics. The quantum mechanics we do, let's make a statement here, remark, we compute quantum mechanics as a Fourier series, quote unquote, right? It's not actually the Fourier series. It's a Fourier series adapted to any given quantum system. That's really what happens when we solve quantum mechanical problems, is we're computing a specific Fourier series for the Hermitian operator in the Schrodinger equation. And then we're using that to decompose our states into, look at that, that's a superposition. We decompose our states into superpositions of basis elements, which are the pure states. Now to that end, I do want to give one other cool example, even though you won't be tested on it or anything. This is the example of the Laplacian, which is the symbol delta, and it corresponds to partial derivatives squared and if you don't know what partial derivatives are, don't worry about it. Basically second order derivatives in multiple directions, so we'll just say two derivatives in higher dimensional settings. So if you look at the Laplacian, on the sphere embedded in 3D. Okay, so we're just talking about take a sphere. Here's my three-dimensional axes. I'm going to draw a sphere on here. So we've got a sphere. We're going to compute this operator, and it's really on, functions taking values on the sphere. So you can imagine just like the height of the mountains on the Earth, that's a function taking values on the sphere. So all around the sphere, you have something taking values. And when you act the Laplacian, when you act these multiple directional derivatives on it and add them together, you find out that this is a symmetric operator. Okay, you take my PDEs course if you want to see why this is the case. I go through it all in the PDEs course. But you take a sphere, you take a Laplacian, it's a symmetric operator. The orthonormal basis of eigenvectors or eigenfunctions which diagonalize this operator are the spherical harmonics. It's a special name for them. Don't worry too much about that name. What I want you to worry about is this picture. So here's the picture of the spherical harmonics. Do these look familiar? And perhaps they look familiar to chemistry students. So hopefully you've taken a chemistry course. S, P, D, F. These are the orbitals, electron orbitals, of a simple atom. Okay, simple meaning maybe hydrogen or something else that's not really bonded to anything else. But when we just look at the orbitals of a single atom, S, P, D, and F, these actually 100% correspond to our periodic table. If you look at the first row of the periodic table, there are 2 entries in first row. If you look at the second row of the periodic table, there are 2 entries corresponding to s orbitals, and then there are 6 entries corresponding to each of the p's. And the reason why there's 2 right ways, you can fit 2 electrons, spin up electron, spin down electron. You can fit 2 electrons in each of these 3 settings, spin up, down, up, down, up, down. So you have 6 entries plus 2 from the s orbitals. So you have a total of 8 elements in the second row. You actually have to jump down 2 more rows to the fourth row. You end up with 8 plus 10, you end up with 18 entries in the fourth row. And come the sixth row, you end up with another 14 plus those previous 18. You end up with 32 entries starting in the sixth row. And so these, which come completely from mathematics, we're just looking at the Laplacian acting on functions on the sphere. And you decide to decompose it and you exactly recover reality. You recover atoms and their orbitals. It's absolutely fantastic. Anyway, we're going to stop with that. Think back to the first 2 exercises for the ones you'll see on quizzes. So look there, but be fascinated by what comes else. I'll see you in the next video. Bye.